Now we will study that how the alternating circuit when only the resistance is connected in it behaves. Okay, so let us consider that there is an alternating EMF which is given by the equation E equals to E naught sine omega t. Now here in the circuit you can see that here one resistance is shown of resistance. One resistor is shown of resistance capital R, and this is what the alternating EMF is. This is how we denote the alternating EMF. Let us consider this alternating EMF is given by E equals to E naught sine omega t. Now, if this is the equation of alternating EMF, and suppose that a resistance capital R is connected, a resistor of resistance capital R is connected there. So we know this that by Ohm's law V equals to I into R. So we can write it as E equals to I into R here. Okay, and then we can write E is E naught sine omega t, and it is equal to I into R. Now what we can do is we can write it as this implies I is equals to E naught upon capital R and sine omega t. We can assume this that E naught upon capital R is actually I naught, which is also the peak value of the alternating current. It is obvious that I naught would be less than E naught because it is divided by capital R, so it has to be. Also, this implies I is equal to I naught sine omega t. Now you can see here that if you see this equation number 1 and let us write it as equation number 2, you can see that as far as the expressions are concerned, they are similar. They are similar expressions. Sine omega t, here also variation is sine omega t. Only difference is that the peak values are different. So if we plot the graphs of current and EMF, then the graphs for current and EMF would look like this. See, EMF, because its value is higher, its peak value is higher, so we can plot it like this. Okay, and this is the peak value, that is E naught. Okay, and if we have to plot the current, so the variation would be similar. Only difference is that the peak value would be somewhat lesser. Peak value would be somewhat lesser. Except that as far as the variation pattern is concerned, it will be similar. So this is the peak value of alternating current, that is I naught, and this graph is plotted between these quantities EMF and current, and EMF and current on y-axis, and omega t is on x-axis. Okay, so you can write here that EMF and current both are in same phase. Both are in same phase when the resistance is connected in the alternating circuit. Okay, we can represent this variation with the help of a diagram which is called phasor diagram. So let us discuss the phasor diagram here. So how can you represent the phasor diagram? Let us try to discuss this phasor diagram. So phasor diagram is a very simple diagram. In this you can represent the EMF and the resistance like this. Okay, so suppose that this is the EMF, capital E, and this length of this phasor, this is not a vector, it is a phasor. Okay, so this phasor, it gives us the magnitude, length of this phasor gives us the magnitude of EMF. So this is capital E, and it is making a certain angle with this axis. Say this angle is omega t. Now you have to understand this, that if this angle is omega t, it's fine. And as far as the current is concerned, as we discussed this, that E is equal to E naught sine omega t, and I is equal to I naught sine omega t. So actually the angle would be same, but as far as the value, peak value of alternating current is concerned, that would be somewhat lesser than the peak value of EMF. So when we are writing the peak value of EMF, see, this is the peak value, so that has to be E naught. And as far as the alternating current is concerned, its peak value would be this, and that is I naught. Okay, and it is obvious that I naught is less than E naught. Okay, so this is how we can represent it in the form of phasor diagram. Let us now this is how the alternating circuit behaves when the resistance is connected. Let us now discuss the alternating circuit when the inductor is connected. Okay, so when it contains only an inductor, then what happens? Let us try to understand that. So alternating circuit, AC circuit containing inductor only. So when it is containing inductor only, so circuit would look like this. This is the inductor of inductance capital L. Here we have the alternating EMF, alternating source. Okay, and what happens that when the current flows through the inductor, actually alternating current, it gradually increases its value. When it gradually increases its value, then what happens that the change in the magnitude of the current through the inductor is taking place, and because of that an EMF is induced in the inductor. Okay, so let us consider that the applied alternating EMF is given by E is equal to E naught sine omega t. This is say equation number 1. Now when this alternating EMF is applied here, so definitely what will happen, the value of the current in the circuit would change. When the value of the current in the circuit would change, then because of this change, what happens, an EMF is generated here in the inductor, and this EMF is generated in such a manner that it opposes the change in the value of the current. We know that this by the Faraday's laws of electromagnetic induction, that this EMF which is generated, not the Faraday's law but by the property of self-inductance also, that E is equals to minus L di by dt. This is what the formula for the EMF which is generated. Now this is equation number 2. See, if the current is flowing through the circuit, then there is a condition for current to flow through the circuit, and it is that this applied alternating EMF should be equal to negative of the EMF which is induced here. Capital E should be equals to the minus E. It means that EMF can be opposite in direction but equal in magnitude of the applied alternating EMF. Okay, if it is, then you can substitute these values here. So capital E is actually E naught sine omega t, and that is equals to minus small e, that is minus L di by dt. So this minus will become, because minus and then minus will become plus L di by dt. Now what you can do is you can write di by dt, or you can write directly di is equal to di by dt is equal to, this L will come on this side, so it is E naught upon L sine omega t. Can we write it like this? If we can write it like this, now this dt can be multiplied this side, so it gives you omega t dt. E naught by L sine omega t dt. Now what we have to do is, here you can see that we have to find a total current. If we have to find a total current, what we will do is we will be writing total current capital I is equal to integration di. If you are writing capital I is equal to integration di, you can substitute it here, so that will give you E naught by L is constant, integration sine omega t dt, and when you integrate it, you will be getting integration of sine theta would be minus cos, so it is minus E naught upon L cos omega t, but because it was not t, so we have to divide by the coefficient of L, that is omega, so it is minus E naught upon omega L. And as far as this is concerned, now we can rearrange it. I hope it is clear to you. Now when we rearrange it, what we will do is we will assume this, that E naught upon omega L is actually equal to I naught. Okay, and here this, let us assume this omega L as XL. So XL is equal to omega L. This XL is called inductive reactance. It is called inductive reactance, and it has the unit of resistance only. It has the unit of resistance only. So what we can do is we can write I is equal to minus I naught cos omega t. I is equal to minus I naught cos omega t, and this is what we have. Now what we have to do is we are trying to write it in terms of EMF, which we wrote earlier. E is equals to E naught sin omega t. So we will try to write it in terms of sin omega t, so that we can compare both the equations. This was equation number 1. So for that, what we are doing is we are writing it like this: minus I naught, and we can write it as sin 90 minus omega t. Now we could have written sin 90 plus omega t also, but I am still saying we are writing sin 90 minus omega t, because we know that sin 90 minus omega t is cos omega t. We are not writing 90 plus omega t, because this minus sign also we have to adjust. Okay, so we know one more property. What is it? It is sine of minus theta is minus sine theta, and this property we will apply. Sine of minus theta is equals to minus sine theta, and when we apply this property, then we can very easily write it as I is equals to I naught, and this minus is multiplied inside, so that will give you omega t. Minus was there, but when minus is multiplied, it becomes plus omega t minus pi by 2. So this is the equation. Say this is equation number 2. Now if you compare 1 and 2, you will be getting that, see, E is equals to E naught sin omega t, and I equals to I naught sin omega t minus pi by 2. What does it mean? It means that here the current is lagging behind the EMF by angle pi by 2. Current is lagging behind the EMF by angle pi by 2. So this is what the behavior of alternating current when an inductor is connected in it. Thank you.